Okay, good afternoon and welcome to a short, hopefully 20-minute overview of Scott Herr's version of what is systems thinking. First question we have to ask is, why do you care? In other words, what's the need for systems thinking? Those of us involved in this grant project feel that there's a need. What is it? Well, Einstein said we cannot solve problems using the same thinking we used when we created them. Therefore, maybe we need a new way of thinking or new problem solving. I think it's better to use all the evidence when you're regarding historical behavior when you're trying to solve a problem, not just the most recent evidence. Systems thinking kind of helps us in that discipline. I also think, and to me what's really one of the more exciting parts, is that it provides a common language for discussing our problems, for looking at alternative solutions, and then the potential consequences of those actions. It's a way to run what-ifs on different potential solutions. First, to clarify, a food systems veterinarian is not just a person who works in the food system. Food system veterinarian is not a computer modeler, so you don't have to be able to play with Stella and at-risk and differential equations. They're not a mathematical geek. Definitely not a predictor of the future, nor is it someone who's just working on food safety. Both of those words begin with S, and people have a tendency to confuse systems and safety, but it's not exclusively food safety issues. A food system veterinarian or problem solver of any type, practitioner, is someone who's thinking with a special problem-solving mindset. They might be working in research, production, safety, policy, anything. As Peter Singy said, they're not taking the straight path from A to B. A food systems vet or practitioner is someone who's habitually using systems thinking, which we will explain. But first, let's think about what is thinking. Sometimes before I come home, my wife calls and tells me about one of my 7 sons and what they may have done wrong. You're not going to believe what so-and-so did today. So immediately I start thinking about how I'm going to handle it. And how do I think about it? Well, I role play. I think about scenarios. When I walk in the house, what's he going to be doing? How am I going to greet him? What I'm going to say? How it's going to go? And obviously those scenarios are simplifications. They only have the nitty-gritty details. I probably don't think about what he's wearing or what music's on in the background, that sort of thing. Therefore, it's a model, which obviously leads us to a commonly made statement by Deming that all models are wrong. Some are useful, and we do have to use them. We're going to use them whenever we think. We're going to do role-playing. We're going to do what? Cause and effect. Well, if I say this versus if I say that, how might it go? That's what thinking is. Systems thinking, and Barry Richmond did a good job, I think, in boiling these down into 8 essential skills. You can find them, same skills, I think, framed in different vocabulary and other writings, but these are the ones we're going to use for our veterinary application today. First off, the 30,000 foot or the 10,000 meter view, where you ask what are the important external forces or inputs, and also what's the boundary of the problem that we're going to talk about today. We think about systems as a cause, or the system as a cause, where you look at the structural relationships. Operational thinking says, how is this thing supposed to work? How is it working? Closed loop thinking asks the question, what factors or drivers impact the input and output relationships that we're interested in? Dynamic thinking asks, what changes have or will happen as these processes continue? Nonlinear thinking says, how will the strength of these input-output relationships change over time? Scientific thinking says, show me the data. Let's test some hypotheses. And generic thinking says, what are the structure and functionalities that are similar to others? There tend to be a set of systems behaviors that can be found in a variety of different applications. And it's interesting, people who are really good at this can walk in and say, oh, that's a such and such sort of systems process. The 30,000 foot view, I think, most good herd health veterinarians are pretty good at this. We ask what's going on, what are the inputs in this operation. I read that, and I think it's good to think horizontally. What's going on the edges of this issue? We all know about corn picker's disease or haymaker's disease. It happens during the harvest season, and there's always more problems with the animals during that time of year because the systems manager is distracted with other things. Also, the 30,000-foot view, we might have to, we'll think about our boundaries there. How big of a problem are we going to attack today? One veterinary example I remember is a fellow in practice who always had these strange cow diseases. He seemed to be a good cowman, but he had some funny problems in this dairy herd. Fortunately or unfortunately, he and his partner broke up, and he did what was rare to do in the 80s, is he just set up a strict milking system. He bought all his feedstuffs, and he did great. He did great with the cows. Well, it turned out he just didn't know how to grow feed. So once he solved that particular input problem, he was on his way. Dr. Alex Ramirez here at Iowa State teaches the students about the 4 circles approach to pig health. First off, do a complete walk around the outside of the building. Maybe we should even walk to the edge of the property. Do a complete walk around the inside of the building. Then a complete evaluation around the individual pen before you get to the individual animal. How many of us as veterinarians are honed in on that individual sick animal? The next systems thinking skill is systems as a cause, where we ask, what are the structural relationships? I like to think about, would we have this same or very similar problem if we had a different infectious agent involved? Some systems examples that I can think of, and I challenge you all to think of some others and add them to the website, are things like, well, we're not weaning enough pigs, or we have a poor conception rate for the beef cows, or neonatal scours, or the prevalence of salmonella at slaughter is 5 times higher than at the farm. Maybe you're not weaning enough pigs because you're not breeding enough sows. Maybe you have a poor conception rate for cows because you don't have enough bulls. Some simple systemic things like that. A good example, I think, of the systems is called what they call the Stanford University prison experiment, where they had these students role play. Some were prison guards, some were prisoners. And it was very quick that those in the prison guard role quickly took on abusive, domineering kind of behavior just because they were given that role. Another way to think about it is how these stocks and flows are connected, and we'll talk a little bit more about what are stocks and flows. Here's an example, I think, of systems as a cause. In earlier studies, it was reported that the salmonella on farms are fairly low. The salmonella prevalence once pigs get to the slaughterhouse is much higher, and most everybody said, well, it's because of the stress of transport. Well, we took that system and broke it up into a few more processes, where we look at the transportation process, and then one that hadn't been talked about a lot, which is the lairage process. As you can see in this figure, on the truck and on the farm, only about 5% of the pigs had salmonella, but once they got through lairage and after lairage, about 40% of them had salmonella. So we found that the lairage was one of the biggest risk factors in this system. Operational thinking. How is this thing supposed to work? Function is the key, not the parts, not the elements. It's really inherent to veterinary medicine when we think about the individual animal. Yet we still boil it down, unfortunately, to a differential diagnosis list. We understand operational thinking when we think, for example, about the cardiovascular system and the respiratory system. If they don't function, if they don't keep in balance, if they don't feed back to each other, things just don't work well. Operational thinking, we want to think about cause and effect relationships. And we think about what's the system supposed to do. So if we talk about the breeding system, what's it supposed to do? Well, it's supposed to make lactating cows. Why? For the babies or so we can sell the milk? Is the breeding system supposed to give us some specialized purebred genetic animals, or is it supposed to give us hybrid animals to be raised for meat? Thinking about those important operational questions help us in our diagnosis and treatment. So now we pause for a minute to think about how to represent a system. And there's some building blocks, some schematics shown in this figure. As you can see here, we've got open females going through the breeding process, becoming pregnant females. Those pregnant females then go through the birthing process, and if we're talking dairy cows, it's also called the freshening process. And we get two outputs. We get the offspring, and we get a lactating female. So you'll see in that figure a few elements that we'll talk about a lot. Stocks or state variables, and they contain a quantity of units, the number of open animals, the number of pregnant animals. And then there's flows or processes. And in my previous, no, skip that. Flows or processes which represent a change or a movement from one state to another. There also are going to be what comes out of a process is an output. What goes in is the input. And then we have converters, which are those little circles. You might think of them as coefficients as you would in a regression equation. And those are the multiple factors that help describe how this flow goes. And then overtly or not is the boundary. I mean, there's the edge of a paper, there's the edge of the problem, there's the edge of a farm, there's the edge of how much we can do on this particular problem today. Just to emphasize, operational thinking to me is all about change. It's all about transformation. So when you go into a problem, ask yourself, what are the changes? What's supposed to be happening? So if we're talking infectious diseases, we have susceptible animals changing to infectious. Infected, change to immune. Sick, change to dead. If we talk about the finishing barn, then we're converting feed to body weight. In the packing plant, we're converting live animals to carcasses, carcasses to meat, meat to human illness with foodborne pathogens potentially. If we're looking at the foodborne illness system or factory, or that we convert open animals to pregnant, milking to dry, unvaccinated to vaccinated, and so forth. So operational is about change.